Hello students, today's topic is determination of rate equation and I will determine it with the help of steady-state approximation. The first problem given is 2a reversible x and this is the first step and you can see that it is a reversible step. So, we will have a equilibrium. Now, this first means the equilibrium has been achieved very fast and it is characterized by the backward constant k minus 1, the forward constant k1. So, we will have an equilibrium constant k1 which will be given by k1 by k minus 1, that is forward rate constant by the backward rate constant. Now, x is the intermediate and it reacts with the reactant B in the next step, which is the slow step, that is rate determining step, and having the rate constant k2 it yields y, it is the another intermediate. Now, it again reacts with another reactant B and it set up another equilibrium which is also achieved very fast and it is characterized by the forward rate constant k3, backward rate constant k minus 3, and we will have a equilibrium constant for this reversible reaction. So, it will be k2 equals to k3 by k minus 3. Okay. Now, first you have to design a energy profile diagram. Now, that is not the requirement. They have not told you or asked you to draw the energy profile diagram for this mechanism. If they ask you, then you will draw this. But to fill the mechanism, if you draw it while in home, you will have a better understanding on this concept. So, what is first step means? First step means that it is associated with a very low activation energy. So, low activation energy means the thermal energy present in the system is more than sufficient to make the molecules eligible for crossing the barrier. So, we have a fast reaction, and slow step means it is associated with a very high activation energy. So, that the thermal energy present in the system is not that efficient to make the molecules eligible to cross the barrier at a time. So, there appears a slow rate and this step 2 of this mechanism progresses with a moderate rate or slow rate. Now, the last step of this mechanism is also fast. So, it is also associated with a very low activation energy. So, how can I draw this? Now, step 1 must be associated with a very low activation energy. For the first step, it is less. This is for the second step. It is large. And it is for the third step, it is also small like the first one. So, we have 3 steps. In the first step, we have 2a reversible x. So, it will be 2a reversible x. This is the intermediate, this is the transition state. Now, x is reacting with B, B is present in the reaction vessel. So, x is reacting with B and is crossing the maximum barrier, that is the barrier having the highest activation energy, and it is passing through another transition state and giving the intermediate y. It is giving the intermediate y. It is the slow step, means it has high activation energy. Now B is present in the reaction vessel, so Y is again reacting with B and it is crossing the last barrier, which is also small, hence it is in equilibrium. So this is the energy profile diagram. Now let us add this reaction. Let us add these steps. So in the left hand side we will have 2a, this x will cancel, this y will cancel, so it will be 2a plus 2b arrow p. This is the overall reaction. So what will be the overall rate of the reaction? Rate equals to K observed into concentration of A to the power alpha into concentration of B to the power beta, where alpha is the order of the reaction with respect to reactant A and beta is the order of the reaction with respect to reactant B, and alpha plus beta is the overall order of the reaction. Now if the reaction has happened in a single step, then obviously alpha equals to 2 and beta equals to 2. So the stoichiometric coefficients, that is the molecularity, will be the order of the reaction. But here, as the mechanism suggests that it is not a single step reaction, rather it is a multi-step reaction. So order may or may not be equal to molecularity. So you have to find it. That is the purpose of this lecture, and let us first predict what may be the rate equation, then I will come to the deduction of that topic. So you can see that this step has a very small activation energy. So this B will have no role in crossing this barrier. Since this step has a very low activation energy, the thermal energy present in the system will be more than sufficient so that this B will cross this barrier with ease and no contribution of B will appear in the rate equation. So to a good approximation, we can predict that we will have order of the reaction with one of the species B to be 0. This is for the third step. Now we have another appearance of B in the second step, that have a very high activation energy. So this contribution must be taken into consideration. So it will be to the power 1. So there are 2 B here. Contribution of this B must be granted and contribution of this B must be neglected in the barrier crossing process, since this B appears in the rate determining step having the high activation energy and this B appears in the first step having the low activation energy. So this is the picture. Now what about the contribution of the reactant A? This reaction rate will depend on X, since X appears in the rate determining step. Now this is a very fast step since it has a very low activation energy. So as soon as we start the reaction by taking A, it will rapidly convert to X. So the appearance of X is actually the appearance of these two A. So you can feel the system like this X has contribution and this X is coming from this 2A rapidly. So actually this 2A will have the contribution. So we can predict to a good approximation that the order should be like concentration of A whole square, concentration of B to the power 0 for the third step and concentration of B to the power 1 for the second step for this one. Okay. So what will be the overall order? This one becomes 1, so it will it will left only. So, the order of the reaction is 2 with respect to A and 1 with respect to B. So, the overall order of the reaction will be 3. So, this is the theoretical prediction only just by watching the energy profile diagram. Now, what will be the value of K observed? Only a guesswork I am doing. See, this rate constant will not appear since it is the first step and it will not contribute in the barrier crossing process for the overall reaction. So, guys, K3, K minus 3, that is the equilibrium constant 2, it will not appear in the rate equation. This is an intelligent guesswork only. Okay. The real thing it will be obtained only after proper deduction. Now, what about this K2? It must appear since this step is the vital one and has a crucial role in the barrier crossing process. So, this K observed must contain K2, must, but in what form, that we have to determine. Now, what about this X? This X is appearing in the reaction mechanism owing to this equilibrium. There is a rapid establishment of equilibrium between A and X. So, that will be guided by this equilibrium constant K1. So, the role of X is actually the role of A, since A is instantly getting converted to X. So, the rate will depend on X, but to have the rate equation in terms of A, we need K1. So, that will only relate between this X and A. So, there must be another parameter, that is K1 here, but in what form, that is whether it will be squared or it will be square root or it will be multiplied by some constants, that only we can obtain after proper deduction. So, this is a guesswork only, okay, and this guesswork is being possible only after logical interpretation of this energy profile diagram. And where from this energy profile diagram is coming? This energy profile diagram is being predicted through another study of this mechanism, okay. So, let us continue with the derivation. So, what is our prediction? So, rate, that is predicted, theoretical prediction, prediction from physical intuition, it is K2 into K1 and it will be A squared and B. So, the order will be 3. This is our prediction. Now, let us proceed. Now, the rate of the reaction, that is rate of formation of product with time, that is dP dt, it will be given by K3 into Y into B. So, this P is getting formed from the forward reaction. So, it will be and this is the elementary reaction. So, the stoichiometric coefficient, that is the molecularity, will be the order. So, it is given by K3 into Y to the Y third bracket to the power 1 into B third bracket to the power 1. Now, P is getting lost by K minus 3. So, it will look like this. So, this is the actual rate of formation of the product. P is gained by the forward direction and it is lost in the backward direction. So, this is the rate. Now, we have to determine the value of Y and put in this equation so that we will get the rate equation. Now, how to get Y? For this, we will apply the steady state approximation, that is, at first, since this step is fast and this step is slow, so Y will accumulate. This step is fast, and we have the production of y from this x, and when y is very less, then there will be less formation of product, and when y is getting accumulated, then there will be more formation of, more conversion of this y to product. Also, with increase in product, there will be increase in the backward reaction. So, a time will come where the concentration of y will remain constant for a while. That is an approximation, but the approximation is good. This will appear for a moment, and for that moment we can apply to a good approximation that the concentration of y will remain constant over time, so that the first order derivative of concentration of y will be 0. Now, this rate of formation of y or rate of accumulation of y is guided by the second step, that is K2 into x third bracket into b third bracket. So, in this step y is getting formed, and in this step y is getting lost. So, it will be minus K3 into y into b, and in the backward direction again y is coming into the picture. So, it will be K minus 3, sorry, it will be concentration of P. Okay. Now, we have to find the value of concentration of y from this equation. So, we take this expression to the left hand side. So, it will be positive, and then we will find the value of y. So, if we take this expression to the left hand side, then in the right hand side it will be K2 into concentration of x into concentration of b plus K minus 3 into concentration of p, and in the left hand side we will have K3 into concentration of y into concentration of b. So, we are taking this K3 and concentration of b to the right hand side. So, it will be like K3 into concentration of b. Okay. Now, we will put this equation, this expression for the concentration of y in this equation. So, it will look like dp dt equal to K3 into b, K3 into b. Now, we put the value of concentration of y. So, it will be K2 into concentration of x into concentration of b plus K minus 3 into concentration of p by K3 into b. We are putting this concentration of y here. So, we have minus K minus 3 into concentration of p. Okay, now this term and this term cancels out. Okay. Now, you can see that what I have told is justified. See this K3, this b is appearing in the first step, and in the first step we have a very low activation energy, so that the barrier crossing process for this step will not depend upon the concentration of b, and you can see in the mechanism that this K3b and K3b is cancelling out, so that this b will not appear in the rate equation. So, with respect to the b that is appearing in the third step, the order will be 0. It will have no role in the barrier crossing process. So, what I have told is being perfectly in good agreement with the derivation. So, this mathematics is taking this fact into consideration that the species which will appear in the first step will have no contribution in the barrier crossing process and will not be reflected in the rate equation. Okay. So, we have K2 into third bracket x, that is concentration of x into concentration of b, and it is K minus 3 into third bracket p minus K minus 3 into concentration of P. So, these two are cancelling out. So, what is left is K2 into concentration of X into concentration of B. Now, see, this is the first step, and here we have an equilibrium. So, the equilibrium constant will be given by concentration of X, that is concentration of product, by concentration of reactant raised to the proper powers. So, what will be the concentration of X? That will be K1 into concentration of A squared. So, you put here K2 into, what will be the value of concentration of X? It will be K1 into concentration of A squared. So, it will be K1 into concentration of A squared into B. Look, this is the value of X. So, here we put K1 into A squared, here is K2 and here it is B, or dPdt equal to rate of the reaction, that is given by K2 into K1 into concentration of A squared into concentration of B to the power 1. So, this is as per with the theoretical prediction. This was actually K observed. So, K observed, that is the observed rate constant, is given by K2 into K1. That is the rate constant for the overall reaction, that is the overall rate constant will be guided by the rate constant of the slow step, and it will depend on the equilibrium constant, since X appears in the rate determining step, but X is actually reflected as A. So, we have to convert X by A, and that conversion is being carried out by this equilibrium constant. So, this is the rate equation. In this way, we have to determine the rate equation from any given mechanism with the help of steady state approximation. So, this is the solution of the first problem. Now, obviously problem 2, you have to do it of your own. Now, solve this and please post the answer in the comment section. First solve it and make it, take a clear photo and make it a PDF, upload it to Google Drive and then post the link in the comment section. I will check it. Okay, so this is your homework. Thank you.